The next type of input we're going to consider is our ramp input. And so again, we're going to consider this as the input to our unity feedback system. So our general equation from the previous video, again copied here, shows our steady state error as t goes to infinity, which is related to our r of s, which is our input, and our g of s, which is our open loop transfer function. And now in this case, because we have a ramp input, we're going to say that our r of s is equal to 1 over s squared. And again, remember, this is for our unit ramp input. So unit ramp, and so because of that, we have the 1 in the numerator. If we had a gain, that 1 would just be replaced with whatever our gain is. So in general, we could call that k. All right, so plugging that in, we now have our steady state error, e of infinity, is equal to e ramp. So try to be more consistent with this notation. So e ramp of infinity, which is equal to the limit as s goes to 0. And now we have s times 1 over s squared divided by 1 plus g of s. So our s is going to cancel out with one of these two s's in our s squared. That remaining s is going to come down and be multiplied by the denominator. So we end up with the limit as s goes to 0 of 1 divided by s plus s times g of s. So as we did with the last time, we can sort of bring that limit just to the denominator because, of course, limit as s goes to 0 of 1 is just 1. And we see with this first term, this s, of course, that's just going to be 0. So really all we need to focus on is this s times g of s. So what we can say then is that our error for our ramp input as t goes to infinity, so our steady state error, is going to be equal to 1 divided by the limit as s goes to 0 of s times g of s. And so this is going to be our equation for, again, we have several things to keep in mind. This is for a ramp input to a unity feedback system, and so more specifically, it's for a unit ramp input. Again, if we had some gain on that, we would just input our gain k there. Okay, so just like with last time, we can say what sort of qualities do we need to have in our g of s in order to obtain a 0 steady state error. So just looking at our circled equation above, we can say for that steady state error, e ramp of infinity to equal to 0, we must have that limit as s goes to 0 of s g of s be infinity. And so really similar to what we saw with our unit step input, the only difference is now we have this s sort of tagging along here as well. So just like what we did with our unit step input, let's go back to the generalized equation for our g of s. So we have our zeros in the numerator, our poles in the denominator, as well as that s to the n term in our denominator, so our poles at the origin. And so for this case, what we can say is that if we want to have 0 steady state input, so for e ramp of infinity equal to 0, we need to have our n greater than or equal to 2 now. So n has to be greater than or equal to 2, whereas before with our step input, we only needed n greater than or equal to 1. And so remember, we can say that in a couple different ways as well. This corresponds to having at least 2 poles at the origin in our g of s. So at least 2 poles at the origin for our g of s. Or we could also relate that to our time domain using Laplace properties. We can say that's the same as having at least 2 pure integrations in g of s. And so again, keep in mind that all 3 of these things are the same thing, just stated a little bit differently. So similar to what we did with our unit step response, we can say, well, what if we don't meet that condition? What if, for instance, we have n equals to 1? So let's say we don't meet that greater than or equal to 2 requirement, but we have n equals to 1. So in this case, what we're going to have is we'll have the limit as s goes to 0 of s g of s. Well, if we only have 1, then this s to the n is going to be just s, and that's going to cancel out with this s here, and we're going to end up with what we saw with our step response with n equals to 0. which is just the product of our zeros in the numerator, z1, z2, and so on and so forth, divided by the product of our poles which aren't at the origin, so p1, p2, so on and so forth. And so in this case, what that means, if we have n equals 1, we're going to have some finite steady state error. So n equals 1 corresponds to finite steady state error for a ramp input to our unity feedback system. Now that we have sort of more ability to go down still, we can say, well, what happens if we have the case of n equals to 0? And so again, we're just adjusting this, this coefficient up here, or not coefficient, this exponent up here. So we have s to the 0, so that's just going to become a 1. And so now we're still going to have this s up here. And so what we're going to see is that limit is going to go to 0. So we have the limit as s goes to 0 of s g of s. And so now we have this s out front, which is not being canceled out by anything. So ultimately, this is just going to be 0. And so we go back to this equation up here, and if we plug in 0 for this limit, we have 1 over 0, which is going to be infinity. So in that case, we have an infinite steady state error. And so in the next video, we'll look at the last of our 3 common inputs, which is our parabolic input.